This problem says verify the intermediate value theorem for the function f of x equals x cubed plus 1 on the closed interval from 1 to 2. Let's start with the statement of the intermediate value theorem, which I'll follow up with an informal description. This is the statement. If f is a continuous function on the closed interval between a and b, and if the value f of a is not equal to the value of f of b, then the function f takes on every value between f of a and f of b on the closed interval ab. So here's a sample diagram. If the function f is continuous, and we'll further define continuous over a closed interval in a moment, but basically, if the function is continuous over this whole closed interval from a to b, and f of a is not equal to f of b, then every single value between f of a and f of b will have some value in this interval, call it c. Let's say we were interested in this value right here, w. If w is between f of a and f of b, for any value between f of a and f of b, there will be some value on this closed interval such that f of c is w. And the phrase continuous on a closed interval ab means that some function f is continuous on the open interval ab, and if the limit as x approaches the lower bound a from the right equals f of a, and if the limit as x approaches the upper bound b from the left of f of x equals f of b. So this means that the closed interval is all of this, and you can get arbitrarily close from the right of the lower bound, but you don't care about anything to the left of the lower bound. And you can get arbitrarily close to the upper bound from the left, but you don't care about the right of the upper bound. So for each of these points inside of the interval, the function is continuous. And now we'll talk about what it means to be continuous at a point. And these are the criteria. If it meets all three of these, then the function is continuous at a value c. So first, f has to be defined on an open interval containing c. So if here are all the values, and here's c, you have to have some open interval containing c, that f is defined on this whole open interval. And now the limit as x approaches c of f of x has to exist, has to be defined, and also the limit has to exist. But I'll mention, you remember that when you're just speaking about a limit, when you're not talking about continuity, you don't require that the function exist right at c. So there could be a hole right there. But this third criteria is that, the second criteria is that there is a value. And the third criteria is that the value at that point C for f of x to be continuous at c, the value of the function at that point has to equal f of c. So we want to show the intermediate value for this function. We want to show that for every value between 2 and 9, because f of 1 is 2 and f of 2 is 9, we want to show that for every possible value between 2 and 9, there is a value on the closed interval between 1 and 2 such that f of that value is the one that we are interested in. Since this is a polynomial function, we won't go worry about verifying that a limit exists on this closed interval, because we have seen a previous, well, you might have seen, there is a theorem that proves that for all polynomials, they are continuous, and for every a in the real numbers, the limit as x approaches a of any polynomial function equals p of a. So for every point on the real number line for a polynomial function, the limit is defined, and it also equals the value at that point. And consequently, the limit going from the right exists, and the limit going from the left exists, and it is equal to, so the limit exists on a closed interval. That was one of the criteria for the intermediate value theorem. Now, to show, let's pick some random w on here. So we say w is between 1, greater than or equal to 1, and less than or equal to 2. Okay? Then we can subtract, oh, I made a mistake. We're talking about w here. We want to say that w is on the closed interval between f of 1 and f of 2. So w is between 2 and 9. Now, my technique is to go from this to c is between 1 and 2, because I'm trying to find out that there is a value in c on 1, 2, the closed interval. But I start with this. I say w is any value between 2 and 9. I'm going to work back this, because w will be equal to c cubed plus 1. First of all, let's subtract 1 from everything here. 2 minus 1 is 1. And you've got w minus 1. Then you've got 9 minus 1 is 8. Now, if c cubed is equal to w minus 1, to get c, I need to take the cube root of w minus 1 equals c, right? So let's take the cube root of 1. We're taking the cube root of everything here. So we got the cube root of w minus 1. And we take the cube root of 8. The cube root of 1 is 1. The cube root of w minus 1 is c. And the cube root of 8 is 2. So we have arrived at, if we said that w is between 2 and 9, then c is in the closed interval between 1 and 2. And since this is a polynomial, we said that the intermediate value theorem can be applied. So we used the intermediate value theorem. This problem says, is the function f of x equals 1 if x is not equal to 3 and 0 if x is equal to 3 continuous at 3? So think about this, and if you need to review the definition of continuous at a point, what that means, we're going to do that in a minute, but as we go, if you remember it, think about it. Here, let's draw a picture of this function. Let's say that this is 1, and here's 0. This is 1, 2, 3. Let's draw a little bit more. So the function says its value is 1 if the value of x is anything but 3. But if it is 3, then the function's value is 0. So we know that right here we have a single point where the function's value is 3. But everywhere else, its value is 1. So what is the definition of continuous? Here's a standard stating of the definition of continuous at some value, say a. F of x is continuous at a if these three things. Is it defined on an open interval containing a? So is there an open interval that you can say around 3 so that the function has a value for every value of x in this open interval? Yes, because there's no value of x in this region where the function has no value. There's no vertical asymptote. There's no, like, square root of a negative number. There's no division by 0. So this one is met. This one says, does the limit as x approaches a of f of x exist? And remember what this means. Is there a region where, or is there a value that you can put plus or minus some epsilon? However small, so that if the difference between f of x minus L is less than epsilon, then there's definitely a region around except possibly right at a. If you remember to say except possibly right at a, then yes, the limit exists, because we can make this as small as we want, and there will be an open interval around 3 where if x is in that interval except right at 3, then the value of the function will be in this little region. So yes. But this one, so as we can tell visually without doing the definition, epsilon delta, we can tell that the limit as x approaches 3 from the left or the right, we can tell that the limit as x approaches 3 of this f of x is equal to 1, because that's the value that you can make as close in epsilon plus or minus 1, so that if you make a x plus or minus 3 is less than a delta, then the value will be in this region. But is the value right at 3 equal to the limit, which is 1? No, because the function says when f of x is 0 when x equals 3. So because it did not meet all 3 of these criteria, the function is not continuous at 3. Commonly stated way of being able to tell is if you ever have to pick up your pencil or pen or drawing instrument to make the function, that's an indicator that it's not continuous at that point where you had to pick up your pen. But this is the continuity test. This problem is a proof problem where you have to read and understand the condition or the antecedent, the if, and then you need to figure out how to mathematically state the antecedent, and then you need to show through valid steps that if that's true, then the conclusion is true. So let's read this. If f of x is continuous on an interval containing c, and if f of c is greater than 0, prove that f of x is positive throughout an interval containing c. I think it's worthwhile to pause this and then read this statement, this implication, very closely, because there's a lot going on here. I'm going to underline the parts that need to be stated mathematically, or at least that I believe need to, before we go about a technique to prove this. So, first thing I've underlined is continuous on an interval. I'm going to call this 1. I'll put those signs right here. I'm going to consider this one a different, although it'll probably be part of it, but I want to show not only any interval, but an interval containing c, and then if f of c is greater than 0. You could consider and an important connective logically, but I'm going to go ahead and know myself that we are talking about both of these. So these are the if, and this is one big thing. F of x is positive throughout an interval containing c. That's 4. This is just a technique that I sometimes use when the problem is to prove something and the if is very lots of concepts to remember. So if 1, it's continuous on an open interval. 2, that open interval contains this c value. And 3, if f of c is greater than 0, then f of x is positive throughout an interval containing c. So here's continuous on an interval. F of x is continuous on an interval AB if for every point P in AB, and look here with these curved lines, what I'm talking about in this case, since they didn't specifically say a closed interval, I just assumed that they meant open intervals. So f of x is continuous on an open interval AB if for every point P in AB, whether it's this point or this point or this point. Let's say I'm specifically curious about this point. For every point in this open interval, f of x is continuous at that point. And we just talked a minute ago about what the criteria for continuous is. The function is defined on an open interval containing that point, and the limit exists, and the value of the limit is the value of the function. So if you have the function, the limit as x approaches p of f of x equals f of p for every point in this interval, then you can say it's continuous on that interval. The next part that I underlined from the problem statement was the continuous open interval contains C. So let's say that C is this one. C is not one of the endpoints of the open interval. And the third part from the problem statement that I underlined was when they said, okay, f of c is greater than 0. So what I've drawn here is a bit of the graph of the function, but I haven't assumed anything about the function except that the value at c is above the x-axis. When I complete drawing the function, it could be a function that goes like this, or it could be like this, or like this. But definitely at this one point, they said that the value of the function at c is greater than 0. And we also know that it's continuous on an interval, some interval, containing this value c. So we know that in this interval and in any subinterval within this interval, the criteria for the continuity will apply to every point in such open interval. Mainly, it's defined, the function exists on this interval, the limit exists, and the value of the function as the limit approaches every point is the value at that point. Now let's remember what was the conclusion that we're supposed to prove. Now these are the exact words from the part of the problem statement. And if you look close, you'll see that I tried to emphasize something with italic text, and it's a detail that I think is important. We're supposed to prove that f of x is positive throughout an interval containing c. The problem did not say it's positive throughout the same interval. And as I was saying a moment ago, there could be other intervals within that contain c. So before we do the actual any type of proof, let's just look at, and this is not a proof, let's draw possible, there's an infinite number of possible functions, but let's just draw a few. If the function were always positive, then it would be true that for every interval, f of x is positive throughout, so that if the function were negative and then it got positive before it even went into the open interval that we established exists in the first part of the problem, and then it went negative again after, then we could prove that the function is positive throughout this whole open interval, which would follow, then this consequent would be true. Look, it is positive throughout an interval. It's positive throughout the whole interval AB. What about this, though? What if the actual function was defined on the whole AB, but it was negative for this part, and then it got positive, and then it stayed positive? Can you see an interval containing c over which f of x is positive for all the values? What about this? What about this interval? Okay, so it is. It's positive in that whole interval. What about if f of x looked like this? It's much less of an interval, but is there a interval over which this function is positive for every value in that interval? There still is. What if I made it an interval like this? Because we said it's continuous from all the way from here to here. The question is there any way where the function is continuous over this whole region, and we said that it's positive for this one value? Is there any way that you can draw the function so that there's no interval that you can possibly draw where it's positive for every value in addition to c? Let's assume the opposite of that. Let's assume there exists some, do I want to say it's some? What I want to say is the opposite of this. There does not exist an interval What I wrote here is, let's assume for a moment that there does not exist an interval containing c. There does not exist an interval around c with f of x positive throughout that interval. Then that would mean that there is some value of the function in this interval around c. With a negative value. But remember, this function is continuous over this whole region. So to get from here to here without lifting your pen, can you do it? It would be hard to do. Can you think of a way so that this function is continuous? You never lift your pen while drawing this function. At this one point, it's above the x-axis. Is there any way to draw it to get below the x-axis without having a continuous line? So to say there does not exist an interval containing c with f of x positive throughout that interval, there must be a point at which it gets from positive to negative without having any other positive values on its way. But if that were true, let's zoom in right here. Let's say that we're looking at this one right here. Is there any way to get from here to here without having some positive values? Because if it's like this, you could draw your open interval boundaries right here. If you say, no, I want to put it even closer, I want to put it right here. But still, there will be some positive values on its way. So to say there are none would mean that the value must be positive and negative at the same point. But that's a contradiction, because we're talking about a function. It can only have one value at one point. So there's a saying that the value, saying that the assumption, we're doing a proof by contradiction. We're assuming that this is not true. and trying to show that that leads to a contradiction. Let's put it this way. Is there any way to say that the value is not, there's no interval containing C with all positive values in that interval? Can you get from here and have a negative value while still maintaining that the whole function is continuous on this interval? That's the contradiction. And so if the opposite of the conclusion leads to a contradiction, then the opposite conclusion is false and the original conclusion has to be true.